Hello everyone, and thank you for joining this webinar. Today's presentation is entitled Beyond Metals, Polymeric Solutions for Structural and Thermal Applications. What we're really going to be talking about is whether it's possible to replace metals with high-performance thermoplastics, and if you can do that, why you might want to do that. But before we get into that, I'll just give you guys a brief introduction to LATI for those of you that might not be familiar with us. So LATI is an independent manufacturer of thermoplastic compounds for injection molding. We're a family-owned company based in Italy, just outside Milan, and we're now on our third generation of the Conterno family in charge of the company. So you'll see our current president, Michela Conterno, on the right there, sitting alongside her immediate predecessor, her father, Professor Conterno. This year is a special year for LATI because it's our 80th birthday. So we've had a number of events throughout the year, and there'll be more later on this year to celebrate the past 80 years, but also to look ahead at what the next 80 years might bring. LATI's a small-sized multinational company. So in numbers, what we mean by that is we have the capacity to produce around 40,000 tons of specialist thermoplastic compounds a year. We have a turnover of around 200 million euros, around 300 workers across the globe working for us, and we can produce materials across 3 production plants in Italy and in China. And we like this size. We think this size is important, and we think this is a good size to be, because it means we're comfortably large enough to support high volume applications, but crucially we're also small enough to retain the agility that we think is critical for responding to our customer needs. So one of the ways that we might do that, for example, is by developing bespoke materials for our customers. So right now, LATI has something like 2,500 formulations on our books. So these are materials that we produce pretty regularly, and a large proportion of these will have been developed specifically for individual customer requirements. The other thing we like about this size is that it gives us the possibility to provide dedicated hands-on support to our customers right throughout the life cycle of projects. So we've got a strong team of R&D guys, technical support engineers who are able to do that. And for us, that means providing this support all the way through a project life cycle. So all the way from initial design stage, all the way through to serial production. But 2,500 grades is a lot to try and get your head around, and I'm not going to try and cover all of those in this presentation. But let's just take a quick look at some of the sorts of materials that LATI offers. And the headline point here is that we focus on high performance materials with enhanced functionality. So if we start by looking at the polymers that we offer, well, it is everything from polyprop to PEEK, and it's semi-crystalline materials and amorphous materials. But for LATI, let's say a standard entry-level material might be something like a 20 or 30% glass-filled nylon, and typically then we would go above that in terms of complexity and performance of polymers. Where we do dip down into the commodity materials at the bottom of the polymer pyramid here, it would always be with some other functionality, be that conductivity, flame retardancy, and so on. So let's have a little bit more of a look at what those functionalities are. And again, I'm not going to go through all of these today, but just give you a flavour of some of the more common ones. So let's start then with structural materials, and we're going to look at these in a bit more detail today. So these are grades with very high loadings of reinforcement. So they're designed for the most mechanically challenging applications. So like we're going to talk about today, applications for replacing metals in many cases. Flame retardants is where LATI made its name. So this is our biggest range of materials, flame retardant materials, and it's been that way since the company was founded, more or less. So of the 2,500 grades that we currently produce, around 300 of those are grades with active UL yellow cards, and we have lots of other flame retardant certifications and approvals beside that. And we have grades based on everything from what we might call the traditional halogenated flame retardants and red phosphorus systems, through to systems that are halogen free, red phosphorus free, and increasingly important, grades that are free from antimony trioxide. After the flame retardants, the next largest family within our range is the self-lubricating materials. And again, much like the flame retardants, we have self-lubricating grades based on everything from polyprop at the bottom of this pyramid all the way up to peak at the top. And we'll have multiple grades based on each polymer. And again, like the flame retardants, with the self-lubricating materials, we have different ways of achieving the target performance. So traditionally, lots of self-lubricated plastics are based on PTFE, and certainly we have a number of those in our range at LATI. But alongside that, we also have a wide range of solutions that are PTFE and more generally PFAS free, which is increasingly important for a lot of our customers. We have particular expertise in grades which are electrically conductive or thermally conductive. So the electrically conductive materials are used in applications typically where we want to avoid static discharge, or where we want to provide electromagnetic interference shielding for sensitive electronic components. So these are often used, these sorts of materials in electronic applications or in hazardous area applications, for example. The thermally conductive compounds we're going to talk about more today, but these are compounds used in applications where we want to dissipate heat. So lighting is a common area, but we also use these materials in a variety of other areas where you want to get heat away from other components. So automotive underbonnet applications, for example, is another big area for these materials. We have grades with improved aesthetics. Quite often we combine that with the structural performance. So we have things that are very strong, stiff, tough, but also that you can use for visual quality applications at the same time. LATI takes its environmental responsibilities seriously, very seriously, and one part of this is within our range we have a growing number of compounds that incorporate bio-based or recycled content. The key point I just want to stress in this presentation is that for LATI, using those bio-based or recycled feedstocks absolutely does not mean that you have to compromise on performance. So what you won't find from us is grades that are on sale just because they are recycled or just because they are bio-based. Instead, what we do is we use those bio-based or recycled feedstocks, and we use those to deliver all of these other functionalities that you see here. So for example, if you're a customer that's historically used a 25% glass-filled flame retardant nylon with full UL yellow card, we can now offer an equivalent to that material with exactly the same mechanical performance, exactly the same fire performance, exactly the same full yellow card, but which incorporates 30, 40, maybe even 50% recycled content. And then finally, to complement our injection molding grades, we now offer a range of 3D printable materials, again offering these same functionalities throughout the different grades of 3D printable materials that we offer. What we focus on is large-scale direct from granule printing. So it has a number of different names, LSAM, LFAM, various others, but the sort of applications where you effectively have an extruder on the end of a robot arm and you're printing large-scale functional parts. So one of the big applications that we're working on at the minute is mold tooling for composites processing. So this is the sort of thing that you might find in high-performance, low-volume vehicles. We also have materials that can be used for large-scale prototyping. So that might be for things like aerodynamic assessments or ergonomic assessments. We have a global presence. We're particularly strong in Europe, but we have direct sales presence in a number of areas, including manufacturing, as I mentioned, in China. We also have a partner in the US that we use for toll manufacturing and distribution, so we're able to offer locally produced, locally manufactured compounds to our customers in the US as well as in Asia. And very recently, in the last couple of weeks, we've just announced a new joint venture with a compounder in India, which again gives us the facility to to manufacture products and supply locally manufactured products to our customers in India and in that region as well. Finally, then, quick look at some of the applications that we support. The biggest area for LATI is the electrical and electronics market. So this is a market with very, very stringent performance requirements, fire performance typically, but we also have applications here for self-lubricated materials. We're talking about parts that also have typically very, very tight dimensional tolerances. And we're talking about generally high volume application as well. So high volume, strong technical requirements. Similarly, in appliances, this is another area, again, with very stringent fire performance requirements, but also requirement for very, very high volumes of material. Other areas we work in, HVAC, automotive, so we are IATF certified. We supply a lot of materials into food and water applications, so we have grades that are EU food and water contact approved, FDA approved, and so on. Lighting I've mentioned, and we'll talk about a bit more later. We work in railway, medical, safety, and a variety of industrial applications. So I guess the common thread here is that all of these are demanding applications, high performance requirements, often requiring high volumes at the same time. And as I said right at the start, with LATI, it's not just materials, it's the complete package of services as well. So that might involve things like providing structural analysis, thermal simulations, filling simulations. We'll have a look at some of those shortly also. It might be hands-on assistance with the injection molding process itself. It might be some technical training for our customers. And if we're talking about developing new materials, then that obviously involves extensive R&D work, lab testing, and continuous product tuning. Okay, so that's enough intro for one presentation. So let's get on to what we really want to look at today then. And really it's to try and answer this question. Can high performance polymers replace metals? And we're going to try and answer that question by looking at a couple of case studies. The first one is this robotic stretcher here, and the second one is an LED lighting device. So let's move straight on to the first one. So case study number one is what's called the STEM Spark. It's the world's first robotic electric stretcher. Quick introduction to STEM. So they're an Italian company specializing in retractable steps of various types. So that might be for industrial or marine applications, also for medical applications. So the one we're going to look at here today is this medical application. Yes, for this robotic stretcher. So let's take a closer look at it. So I guess the key features of this are its robotic undercarriage and the ability to handle multifunctional accessories. So to give you a bit of background, this Spark product was originally designed to accommodate highly infectious patients, around COVID time. So you can see here in this picture here, this isolation unit which sits on top of the kind of main body and legs of the stretcher. So it's got all sorts of ports to allow medical professionals to access patients safely, and also to keep those patients isolated at the same time, and various ports as well for connecting different bits of medical equipment and machinery and monitoring and all of these kinds of things. So that was the original intention of this device. And then obviously as that kind of big surge in demand and requirement for isolation kind of tailed off a little bit, as COVID was brought more under control, then this product was reimagined more as a more general purpose multifunction device, and initially designed for the US market. So if you take a look at the STEM website, you can see some of the different variations, different configurations. So on the previous slide we saw, I guess, kind of the more standard stretcher setup. So variations on this sort of thing as well. So some of the key features for this are, obviously we need to, there are going to be some complex patient requirements and associated with that some complex handling and transportation requirements. We're going to be dealing with heavy loads, so of course people come in all shapes and sizes, and that's before we start hanging all of this different specialist medical equipment off of this device as well. So the loads can be quite high. And then as this thing is being wheeled around, placed onto ambulances, taken off, wheeled around hospitals, then there's big possibility for impacts and general mishandling. And one of the key features of the device are its independently adjustable legs for making sure that the patient is in the optimal position. So we'll see it in, let's say, sort of standard configuration in this picture here, but each pair of legs, front and back pair of legs, can kind of splay out independently of each other. So the idea of this is that you can always keep the patient in an optimal position. So okay, here it's shown in an incline, but I guess more commonly you'd be keeping the patient horizontal as the legs adjust to either deal with inclines as you're moving the patient around or getting them on and off an ambulance. So what you need for all of this is you need something that's lightweight. It's got to be impact resistant. So you'll probably see that for the main body of the legs here, if you look a little closer, these are made of carbon fiber material, so lightweight, strong, stiff materials. You need something that's resistant to the cleaning fluids and various other things that you'll find in a hospital setting. And it's got to have this overall structural lightness and impact resistance. So high performance plastics are an ideal candidate for this sort of thing. The part that we're focused on, or we did focus on in this project, is the wheel support. So actually it's a couple of components. I'm just showing one of them in this model here, but you can see that there are two components here, hinged, and really this is a critical part that allows these legs to be raised and lowered while still keeping the patient in this horizontal position and still being able to wheel the thing around. It's quite a large molding, so that brings challenges in itself. So the picture probably doesn't do it justice, but this is probably 30-40 centimeters long, this part, so quite a chunky molding. Of course, it's got to have this static load resistance, but also a creep resistance as well. We talked about impact resistance. Dimensional stability is very, very important. So is it going to retain its shape post molding? Particularly important for two things. So firstly, of course, you've got those two components there that need to be able to freely move past each other. So it's no good if you've got distorted parts coming out of the molding. And then also you may be able to see here, so this section here of the part fits inside the carbon fiber tube of the leg. So again, it's important that we've got tight dimensional tolerances on this so that we can correctly fit this into the leg and connect it accordingly. Aesthetics are also important. Surface finish for two reasons. One, it'd be nice to have something that looks nice, but also there's a more important point of cleanability as well. So smooth, easy to clean surfaces are always important in a hospital setting. And from a branding point of view, the customer wanted to be able to colour this in a kind of corporate colour. So in this project, LATI worked alongside STEM, and we also worked alongside a company called Caproplast. So Caproplast are an Italian injection molding and tool manufacturing specialist. So they worked with us to help design this part and ultimately to produce the components. Step one then is choosing what we think would be a suitable candidate material. And I think fairly obvious looking at the mechanical requirements. We're looking at something from within LATI's structural material range. And the material that we opted to open with here is a material we call Latamid 66 H2 G50. So this is a nylon 66 with 50% glass fiber, amongst other things in there. It's a grade with improved surface finish. It's a grade with very, very good mechanical performance. So strength of above 200 megapascals, modulus around 16 gigapascals, and it does have the excellent creep resistance that we need for this application. just a note, you might be thinking, well, okay, well, why don't we use carbon fiber rather than glass? Too brittle for an application like this, really. So if we want the good impact performance, then typically glass has got better impact performance than carbon. So that's the material. Glass is the reinforcement that we need for an application like this. And for a nylon 6/6, it's got relatively low moisture uptake, this material. So once we've picked a material that we think is a good candidate, then the next thing we would do on a project like this is carry out some structural analysis. So these are some of the loads that we looked at, and some of the requirements from STEM. So we've got static loads, in this case with this component kind of perpendicular to the load. We need to think about lateral loads as well, in combination with those perpendicular loads, and we need to consider all of these different load cases actually with this hinged component in different configurations. So yes, with it, I guess, kind of in what would be the fully flat position, but also in the fully open position, if you like, as well. The customer set some pretty high impact load requirements for this application, and I'll be honest, this was a very, very, very challenging impact load to try and meet. So I think it's fair to say the simulation never quite showed that this was met. It was really a case of getting as close as we possibly could to then enable the parts to go into real world testing with some reasonable confidence that it would deliver the desired performance. So that was really the target here, around this 8,000 Newton impact load. So as we're doing all of this analysis, of course, we're making modifications to the geometry and to the layout of the part. So in this case, we had to look at the layout, positioning, the thickness of the reinforcing ribs to ensure that we get this optimal stress distribution to make sure that the part can withstand the desired loads. And ultimately, we go through several iterations of something like this until we get to a point where we've got a geometry that fulfills as closely as possible the requirements of the application. So, we're now at a point, we have a design, we think it's going to work. The next thing is, okay, well, can we actually make that part? And this is where the molding analysis and tool optimization comes in. And I'll be honest, here in this project, there were a few problems that were detected by this analysis. One of the big problems was differences in volumetric shrinkage. So normally this is something that we'd address by reducing wall thickness, but in an application like this, where we're really, I guess, pushing the boundaries of the mechanical performance that we need, it's not as easy as just taking thickness out of the part. That's not really viable. There were some cooling issues, again, partly linked to differential part thickness here. So you can see significant differences in surface temperature of a part as it comes off the tool. So, as low as less than 80 degrees in some places, but higher than 200 in another. So this is the sort of thing that's obviously going to contribute to significant deformation as you demold the part. So something to be avoided. So if you simulate the deformation that comes from a combination of those two effects above, plus the combination of any fiber orientation that we get during the molding as well, then what we were looking at is something like this, and this is clearly no good, because this is the end where we want to fasten into the carbon fiber legs. And at this point, it's worth saying that this is where it really, really helps to work with a specialist technical molder who's got the experience at working with high performance materials like this. So at this point, really, Caproplast really took over, and using the information that we provided to them from the analysis, they were able to make a number of modifications to get a part that would actually come out looking like we wanted it to. So that involved optimizing injection molding locations to get a better fiber orientation in the part. And the other big thing it involved was designing improved cooling channels to avoid those big fluctuations in surface temperature that we saw on the previous slide. But again, through their expertise, they were able to do all of this, and the result was a compact and relatively lightweight tool to make these parts. And then here's the result. So here are the two components. So we've got a lightweight, impact resistant, corrosion resistant material with good dimensional stability that's able to meet all of the requirements of the stem spark application. So nice part, nice surface finish. So that's case study number one. The second case study we're going to look at is this high-powered LED lamp from Vossel-Schwabe. If you're not familiar with Vossel-Schwabe, they are a technology leader within the lighting sector. So they have a product portfolio that covers all kinds of lighting components. So everything from lamp holders to LEDs to the various bits of electronics that are used around all of that. They're a German company with production and sales sites across the world. And this particular case study is one that we developed with their Italian team. So the product is known as Brave. That's the family name, and it's intended as a modular plug-in replacement for traditional outdoor spotlights. So things like street lighting, industrial lighting, sports facilities, and so on. Some of the key requirements are IP67 rating, so moisture ingress protection and UV resistance. Must have corrosion resistance, so you imagine all sorts of public places with various various fluids and animals that need to be dealt with, and we need to avoid corrosion from all of those sorts of things. So that rules out aluminium in this application. It needs to have a very, very high life expectancy as well. And for LED systems, one of the big factors that can reduce life expectancy and does reduce life expectancy is excessive heat buildup. So this case study then is all about how we can use specialist thermoplastic compounds to dissipate heat. So let's start by taking a look at how these sorts of LED lighting modules are typically constructed. So in the diagram here, you'll see we have the LEDs, surface-mounted LEDs, and electronics here, sitting behind glass. Heatsink is in direct contact behind, and then the whole thing is in a frame, which is then can be mounted to a whole sorts of different housings, let's say, and there's a gasket in there to keep the moisture and dust and whatever else out of the sensitive bits inside. So the key requirements of the heatsink part here, which is what we're focusing on, this heatsink part at the back, it must have outstanding thermal conductivity. So this product is available in a few different configurations, but the highest power one of those is up to 44 watts. So that's quite a lot of heat being generated that we need to get away from the electronics if we want to maximize this lifetime. We must have dimensional stability. So for the heat sink to work effectively, it has got to be in contact with the components that are generating the heat. We don't want an air gap between those two things. So dimensional stability is important to make sure that we maintain that good physical contact. We need an absolutely flat molding. Otherwise, we're either going to have an air gap, or we're going to have to start using thermal interface materials, which adds an extra process, adds extra costs to the production of these units. Dimensional stability is also important because, remember, this is a retrofit device. So if we want to take this and plug it into some existing housing somewhere, it's no good if we've got a variety of shapes and sizes because we've got warped moldings. Chemical resistance, we talked about. Mechanical resistance is also important too. So these units are going to be installed in industrial areas or public areas. So knocks and scrapes, whether accidental or deliberate, are going to occur. We also need to take into account impact resistance as well. In this case, there was a particular drop test that needed to be successfully passed. So again, as we did last time, let's start by looking at what sort of material we might use. And I think fairly obviously here we're looking at something from within LATI's thermally conductive material range. In this case, the grade that we looked at is a grade we call LATI PA66 GF50. So this is a nylon 6 material with 50% graphite in there as the thermally conductive additive. So this is a grade with outstanding thermal conductivity. In fact, it's one of LATI's most thermally conductive grades. It's a grade with improved flowability. So when we look at some pictures later of the part, you'll perhaps appreciate this a bit better. But for applications like this, it's quite common to have complex shapes, lots of right angles and corners in there, sometimes relatively thin sections. So good flowability is critical for these sorts of applications. We've talked about dimensional stability, and this grade is excellent for that, to maintain that good thermal contact between the heatsink and the heat source. Even though this is a highly filled grade, it still does have very, very good mechanical performance. It also has the ability to withstand self-threading screws. Again, particularly important if we're looking at being able to retrofit this thing in a variety of different existing housings. So LATI's done quite a lot of extensive testing looking at different self-threading screws and how well or poorly different materials can accept those. So we have lots of other information available on that. If you're interested, we can make that available on request. So I guess at this point, I usually like to kind of address the elephant in the room. So when we're talking with customers and talking about the idea of replacing metal heat sinks with plastic, the big question that always comes up is, okay, well, can the polymer compound conduct heat as well as aluminium? Well, let's have a look at the data. So we'll look here at the thermal conductivity of aluminium versus a couple of different families of thermally conductive plastics. So the one we've chosen for this application is in this family. So these are conductive materials based on graphite as the conductive additive, but we do have some others which use ceramics instead of graphites. And I'll not go into the details in this presentation, but these have particular uses in applications where you might want thermal conductivity, but absolutely don't want any sort of electrical conductivity. So let's have a look at the thermal conductivities then. So for aluminium, you have a thermal conductivity in planes, so along the length of a part of around 110 watts per meter Kelvin. This is for die-cast aluminium. And because aluminium is an isotropic material, it's got the same properties in all directions, then the thermal conductivity is exactly the same through the thickness of the part as it is along the length of a part. That's not the same with thermally conductive plastics, though. So the first thing we'll note here is that the in-plane thermal conductivity of graphite-filled plastics is generally in the region of just 10 to 30 watts per meter Kelvin. So at best about a third of what we can achieve with aluminium. But because the graphite platelets are they have a high aspect ratio, so their XY dimensions are much larger than their Z direction. They're much longer and wider than they are thick. So that means that very much like glass fiber reinforcements, the graphite material will align to a certain extent during the injection molding process. And much like with glass, how that alignment of the glass leads to some directionality in mechanical performance, well, so with the graphite compounds, alignment of the graphite leads to some directionality in the thermal conductivity. So in this case, we see a big reduction in thermal conductivity through the thickness of the part versus along the flow path of the injection. And things don't look a lot better when we look at the ceramic filled material. So with the ceramics, the additives are more uniform in direction, so we don't get that same directionality, but the thermal conductivity is lower again. We have some other highly specialist ceramics that are have a little bit better performance, but still not as good as the graphite filled materials. So on the face of it, doesn't look so good for the conductive plastics. But the key point to remember here is that for heat dissipation applications, thermal conductivity is not the critical factor. It's not the critical parameter that we need to look at. And actually, we need to think a little bit more about how the heat transfer is actually occurring in these sort of systems. So at this point, we'll take a brief interlude and we'll revisit a little bit of high school thermodynamics and remind ourselves of the different heat transfer mechanisms that are going on here. So first of all, we have conduction. So this is, we've got a heat source and heat is being transferred through some other object. So here's the heat source, here's the object dropped on top, and conduction is all about heat being transferred through this, in this case, this solid object to the surfaces of that object. Then we have convection. So we've got our part that's now being heated up, and convection is all around the heat then being transferred to the surrounding air, or I guess more accurately, the surrounding fluid, whatever that may be. And then finally, we have radiation. So again, we've got our object here, and this is emission of electromagnetic radiation, and this occurs for for any object that's sitting above absolute zero. So let's have a look at how plastics and metals compare in these sort of scenarios. So we've just seen the data for conduction. We've seen that aluminium is miles better than a polymer compound. Now for radiation, it kind of depends, but if we're looking at a natural silvery coloured aluminium, let's say, versus a black thermoplastic, and these are going to be black because graphite is going to give that colour to the final parts, then actually a polymer compound radiates heat better than aluminium. But in heat dissipations like this heat sink that we're looking at, the dominant heat mechanism is convection. We're wanting to take heat from the part and transfer it to the surrounding air. And what we find with this is that aluminium and polymer compounds behave very, very similarly, providing we have a thermal conductivity of around 10 watts per meter Kelvin or above. And as we saw with the previous slide, we comfortably meet that with the thermoplastic. So this is a value that we arrived at through extensive testing at LATI, and also independently extensive testing carried out by Vossel-Schwaber as well, to arrive at this kind of 10 watts per meter Kelvin value. So this is the key thing to remember, really. Don't focus on absolute thermal conductivity. As long as we've got a value that's around 10 watts per meter Kelvin or above, then a thermally conductive plastic can dissipate heat just as well as a metal can. Okay, so I think hopefully we've kind of convinced ourselves that the plastics are a good option from the point of view of low corrosion, lightweight, and they can do the job from a thermal conductivity point of view. It's also worth having a look at how they perform environmentally as well. So plastics get a bit of a bashing most of the time. Sometimes it's justified, often it's not. So let's have a look at how the environmental performance of thermally conductive plastics compares with aluminium. So what we'll do here is we'll look at the cradle to gate global warming potential of the different materials. So by that I mean we're looking at the global warming potential of the raw materials as they leave the factory. So the plastic pallets as they leave LATI's factory, but before they go onto the injection molder to make the final parts. And the same with the aluminium. So it's the aluminium as it leaves the refinery, I guess, but before it goes on to the foundry to cast the aluminium heat sinks. So if we look at the global warming potential for aluminium to begin with, it's around 9.7 kilograms of CO2 per kilogram of material, and this is data from the European Aluminium Association's most recent environmental profile report, and this is taking into account the aluminium that's consumed in Europe. So that aluminium might be sourced from all around the globe, but it's intended to represent the product mix that's actually used in Europe. And if we look at the plastics, and this is LATI data, then we see that it's slightly better at 6.5 kilos of CO2 per kilo of material. But actually, this is not really the right sort of calculation, because if we think about it, if we swap out an aluminium heat sink for a plastic one, those two things aren't going to use the same mass of material, because the density of aluminium is almost twice that of the thermally conductive plastic. So a more accurate comparison is to look at not the kilograms of CO2 per kilogram of material, but to look at the kilograms of CO2 per unit volume of material. So if we do that, we get a figure of around 9.8 kilos of CO2 per cubic decimeter for the LATI Contour 62 GR50. And for the aluminium, we're over 25. So much lower GWP for the plastic version versus primary aluminium. And at which point you might say, well, that's great, but nobody uses primary aluminium. Everybody uses some recycled content in there. Okay. But even if we allow for the fact, even if we allow for, let's say, using up to 60% recycled aluminium, we still see a reduction in GWP for the plastic versus the aluminium version. And remember also that this is just cradle to gate, so we're not considering any of the processes that happen further downstream here. So before we consider the fact that the energy consumption associated with injection molding, where we're running machines at maybe 250, 300 degrees C and running tooling at 90 degrees C, is going to be much lower than for aluminium die casting, where we're melting materials at maybe 700 degrees and we have mold tools that are set at around 400 degrees. We also need to consider things like lifetime of the tooling. So with injection molding, we can get maybe as many as 500,000 parts, if not more, from a single tool. With die casting, maybe we might get 50,000 if we're lucky, but then we'll need to scrap that and make new tooling. And it's before we consider things like, okay, shipping parts around the world. Are we shipping some lightweight plastics, or are we shipping heavy aluminium parts? So all of these things, kind of work in the plastic's favour. It's also before we consider any sort of recycling on the plastic side. So here, of course, we've considered using 60% recycled aluminium. What we find is it's possible to regrind and reuse this material with no loss of mechanical performance, no loss of thermal conductivity. So we could improve this even further by taking some reground material from here, as is common in injection molding, and using that to make new parts. And the even cooler thing than all of that is that we now have a new version of this material as well. So in this grade here, all of the nylon 6 is virgin nylon 6. We have a new version where we replace all of that virgin carbon nylon 6 with nylon 6 that's chemically recycled. So this is material that's made from a mixture of post-industrial and post-consumer waste. So it might be nylon carpets, it might be nylon fishing nets, it might be various bits of clothing. All that is broken down back to the monomer and repolymerized to give a 100% chemically recycled nylon 6. We use that to make this version of the same thermally conductive plastic, exactly the same mechanical performance as the virgin grade, exactly the same thermal conductivity. But the GWP is around half of the virgin material, and again we're now comfortably less than half of the aluminium, even accounting for the fact that we use recycled aluminium. So the important point to note here is if we're comparing environmental performance, let's not look at GWP per kilo, let's look at it per unit volume. And you can do the same thing with cost, actually. So if you look at the cost of plastic per kilo versus aluminium, then the aluminium is always going to be cheaper. But if you think about actually how much material is used to make your part, then actually that's a much closer comparison between those two things. Okay, so at this point, plastics, I think we're convinced, will tick the box from the point of view of non-corrosion. They'll tick the box from the point of view of thermal conductivity and from environmental performance. Well, what about fire performance? Well, yes, we can tick that box as well. So as I mentioned right at the start, flame retardancy is where LATI made its name, and it's where we have extensive expertise, and we apply that expertise within these thermally conductive compounds as well. So the full range has UL approval, and we also have UL 94 V0 grades available if required as well. Okay, so we've taken a brief interlude here to convince ourselves that thermally conductive plastics are up to the job technically and commercially. So now let's get back to the part in question and have a look at some molding analysis and tool optimization. And here there are two things that we can do. So firstly, we can carry out the standard mold flow and FEA analysis. And in this case, we highlighted some issues again with the first iteration of the parts. Issue number one, and exactly the issue that we don't want, is some out of plane deformation on the base where the PCB and where the LEDs are going to be mounted. So as we've talked about, very bad news for maintaining good thermal contact. So that's something that needs to be mitigated. And the other thing that we noticed, you can maybe just pick it up on this drawing here, is a bit of deformation around this kind of the rim of the part here. And this is bad because this is exactly where the gasket would sit. That gives us the IP rating and keeps the moisture and dirt out from the electronics. So we need to mitigate this deformation here as well. The other thing that we can do is we can combine mold flow with thermal simulation to help us evaluate the cooling efficiency before we even start thinking about cutting tooling and making parts. So I don't have time to go into all of the detail of how we do that in this webinar. We have separate webinars and separate guidance notes on how we can do that if you're interested. But what I just want to point out here is that for all the reasons that we talked about here, because of this this directionality that we get with graphite type materials, and and how flow paths can affect thermal conductivity, for all of those reasons, then the geometry of the part wall thicknesses, flow paths, they're all going to have a big influence on ultimately what the thermal conductivity of the final part is going to be. So this is just a generic example here, but you can see, just by designing or adjusting how we might design the cooling elements, we get a big difference in these things. So let's say our heat source is down here. We want to get that heat up and away from that source and away from the sensitive electronics. We can see that this kind of thin configuration, generally speaking, is better to do that, because we're getting higher surface temperature here, which is where we want it, up at the top, away from the sensitive electronics below, versus this pin situation where we're not getting quite so much heat being transferred up to the top of these, which means it's remaining down here, which is bad for our parts. I'll just summarize in this slide and say that for this part and the simulation that we carried out here, the simulation was able to confirm that the design would give us the desired heat dissipation and prevent excessive temperatures around the LEDs. And then when it comes to the molding issues, well, I guess here it's worth noting that Vossler-Schwaber did have a bit of a head start here on how to solve some of these molding issues. So this part is not their first rodeo. So Vossler-Schwaber and LATI have worked together for many years now, and they have vast experience in working with our thermally conductive materials. So you can see a few examples of other parts that they have made in the past using these types of materials, and you can get a feel for some of these different geometries that that have been used to give the desired cooling performance. And so it's this vast experience really that helped them to make the various design tweaks, the tooling modifications that were needed to overcome those deformation issues that we saw on the previous slide. So here is the final part. And you can see here again, as I mentioned before, we've got some quite intricate design. We've got quite a lot of corners here, so this is why flowability is important. We've got a nice surface finish. We've got something that's flat. We can mount it into a variety of different housings, and we can tick all of those boxes for thermal conductivity, dimensional stability, surface finish, corrosion resistance, with a lightweight part with lower environmental impact than the aluminium alternative. Okay, so thanks for sticking with us throughout this webinar. Just to quickly summarize then, it is possible to replace metals with high-performance plastics. To do it, you're going to need some special, optimized thermoplastic compounds. So today we looked at structural and thermally conductive materials. We could have picked some case studies for electrically conductive materials, ones with improved aesthetics, high temperature ones, and maybe we'll revisit some of those things in a future webinar. You need to have well-designed components, so it's important to recognize that these high-performance materials, they're not always simple drop-in plug-and-play solutions. You probably are going to need a bit of specialist support to help you design the parts and design the tooling, and that's absolutely something that LATI can help you with. And then you've got to process those materials correctly. So if you're an OEM listening to this, then I would say, you know, working with an experienced molder is definitely a big advantage if you can find one. And we can help you point you in the direction of those people. But if you're a molder listening to this and all of this is kind of new to you and you're wanting to take your first steps in this area, then absolutely come and talk to us, because LATI can help you build that expertise in working with these materials, designing with them, and optimizing geometries and so on. So yeah, please do come and talk to us on that. So if you can put all of those three components together, then absolutely it's possible to achieve component lightweighting, reduced environmental impact, improved corrosion resistance, and you might even be able to reduce costs at the same time. Okay, so thank you very much for listening. If you have any questions, please drop me an email, or we'll take some at the end of the webinar. And for more information on any of the things that you've seen today, please do take a look at the LATI website. Thank you.